Hi, welcome to the next of our series of video lectures. Today we're going to be talking about conductivity, which occurs in metals or other materials in which when electrons feel the force of an electric field, they're free to move. And this changes the way that electric fields respond and materials respond to electric fields. If you're in my class, you can follow along in your textbook by reading section 4-6. So let's say we have an electric field, and of course we're going to call that E, the electric field, and suddenly somehow in the middle of this electric field we're going to put in an object that has conductivity, in which that the charges inside the object are free to move around. Remember, with our dielectrics we had a little bit of motion of charges. The center nuclei of the atom stayed fixed, but the electron cloud shifted just a little bit. Here the electrons can go wherever they want to inside the material and move freely. What happens in this case? Well, this picture up here is not correct. Essentially, what do we get when this happens? Essentially, what you're going to get is that you're going to have, essentially, the negative charges are going to get attracted to the electric field. So all the negative charges are going to rush over to this side because they feel the force of that electric field. The positive charges stay where they are, but that leaves essentially a net positive charge over on this side of the conducting material. So since your electric field lines are going this way, they're going to terminate on a negative charge, terminate on a negative charge, terminate on a negative charge. It turns out that the electric field lines always come in perpendicular to conductors. That one's going to go like that, this one's going to come in like that, that one's going to come and terminate like that. The ones out here are going to feel a little bit of force, but they're going to keep going. Over here on the positive side, the electric field lines are going to come off the conductor, and a new electric field is going to be generated. So all these are going to come off perpendicular and come out sort of in this direction, with this one getting distorted a little bit but missing. And essentially what this means is that the electric field inside the material is much, much less than it was before these conductors moved. It's close to zero. Unless it's a perfect conductor, it's never exactly zero, but the electric field is very, very close to zero. It's very much reduced. The reason for that is if there was an electric field inside the material, essentially what would happen is it would push on these conductors, and the conductors would just rearrange themselves to make the electric field zero, because that's the minimum energy condition of this material. The potential energy is minimized when there's no electric field inside the conducting material. So that's the general case. Let's look at a more geometrically simple case, which is just a conductor. It's a wire. That's the cylinder. So here's our wire that has some applied voltage across it. We put a potential across V with the positive end here and the negative end here, and I'm just going to tie this to ground so we know that we have 0 volts at this place and V volts at this end of the wire. We're going to make a simplifying assumption that because we essentially have an electric field, V equals delta V, that the electric field is pretty uniform through the wire, and it's just going to stretch down the wire in this direction, for example. And that we know if we have a charge inside this wire, and we're going to call the charge Q, that charge is going to feel a force, the electric field is going to push on it, and it's going to move in that direction. And we know it's going to move because any force accelerates a particle, and we know the ratio between force and acceleration is just due to the mass. That's Newton's law. It turns out, as we've mentioned before, that inside wires the positive charges stay fixed, and the negative charges, which are electrons, essentially move. So electrons are going to flow opposite to the direction I've drawn here. They flow into the electric field, but the idea is still the same. And this should all be sounding very familiar to you. This is basic electricity. We want to calculate the amount of charge that flows per unit time through this wire. So we know the wire has some area A, and the number of electrons per second that flow through area A is just the number of electrons per unit volume within the wire. So you can think of that as some cube here within the wire, and basically just calculating the number of electrons that are in the volume of that cube. We multiply that by the velocity, how fast the electrons are moving, and by A, the area. And if we do that, we're going to capture all the electrons that are essentially flowing up through the wire in this direction. Remember, they're flowing this way because they're negative. And when we do that, when we basically multiply the number of electrons per cubic meter, the velocity in meters per second, and the area of the wire A with the amount of charge each electron carries, and we go through all the units, essentially canceling out that meters, and those meters, we end up with the amount of charge per second that flows through the wire, and we call this I, the current. So I is a current, and as shown right here, it's given in coulombs per second. How much charge in 1 second will flow through this wire? And it's good, of course, to remember that the charge on one electron here is basically 1.6 times 10 to the minus 19 coulombs of charge, so it takes a lot of electrons to make a significant current. Well, what if we don't have a wire? What if we have a more general geometric shape, for example? Well, in this case, we just consider a blob of conducting material that might be right here with an electric field going through it. It's not a perfect conductor, so the electric field gets attenuated, but it's going to be in there essentially somehow, and we know it's going to bend itself around the conductor as we saw previously. But in this case, we don't calculate essentially the current through the wire. We just want to calculate the amount of current that flows through some area, and so all we do is we just divide our previous equation by A, and we can find the current density, J, which is the coulombs per second per unit area that flows through the wire. And this current that's due to electrons flowing, or the current density J, is just the charge E, remember 1.6 times 10 to the minus 19 coulombs, times the number of electrons per unit volume, times the velocity of each of these electrons. And again, this is not a current, but it's the amount of current per unit area, or coulombs per meter squared per second. So there have been a fair amount of equations, but what have we learned from this? We know that when electrons move, charges move in conductors, that we measure the number of coulombs, the amount of charge moving per second, and we can represent that as a current, the amount of charge per second if we're moving through a wire or fixed geometry, but more generally we call it a current density, the number of coulombs per second moving through one unit area, and we call that number J. So J and I are both interchangeable. You'll notice that they're both vectors because the current does have a direction to it. Although, to be perfectly honest, many times when we're talking about current moving inside a wire, we just give I and don't put the vector sign over it because the wire constrains the direction that the charges will move. But since J is more general, we always treat J as a vector. To tie this back a little bit more closely to the idea of electrostatics, of charge, of voltage, of electric field, let's take a look at the acceleration that a charge might feel in an electric field E. We remember that the charge, or the force on a charge, is simply the force is equal to the charge times the electric field, and that the force is also the mass times the acceleration. The mass of an electron is very, very tiny, 9.1 times 10 to the minus 31 kilograms, at least at rest. And we also know from our freshman physics that we can relate the acceleration to the velocity and to the position of a charge. So let's do some simple calculations and see, as a function of electric field, how fast is the electron going if we accelerate it from rest to have some velocity v after traveling a distance of 1 meter. So what do we come up with when we do these calculations? It turns out that if E is 1 volt per meter, you're moving very, very fast, about 4 times 10 to the 5th meters per second in a material, and this is very simplified. The mass of electrons actually depends on the types of materials they're in, but ignoring that and assuming the rest mass of an electron, this is what you come up with. For an electric field of 100 volts per meter, you get 4 million meters per second. 10,000 volts per meter, you essentially are going to get 40 million meters per second. And if you come up with an electric field of 1 million volts per meter, you get 400 million meters per second. And it may seem that this is ridiculous because an electric field of 1 million volts per meter is really, really big. I mean, 1 million volts is a lot. But it turns out in semiconductors and really small things that this is just a voltage difference or an electric field of 1 volt across 1 micron, 1/1,000,000th of a meter. And those are actually pretty big sizes in modern semiconductors. So high electric fields certainly are possible inside devices. And at this point, some alarm bells should be going off inside your head, because this number is faster than the speed of light, and we know the electron is not going to accelerate to anywhere near this speed. Simply because of relativity, the mass of the electron will get heavier. Lots of weird effects will kick in that we're going to talk about later in another couple of video lectures. But right now, we need to understand why this isn't happening, why the electron can't accelerate faster than the speed of light. So in order to do this, let's zoom in a little bit, and we'll have our conducting blob of material, and we'll put an electric field across it really quickly, and then zoom in to see what this looks like on a microscopic scale. And what you find is essentially you have a bunch of nuclei of atoms, which are these red circles right here. Let me use different colors so they show up a little bit better. These are the nuclei of atoms, and they're surrounded by this cloud of electrons, which is this kind of greenish looking mass here. And these electrons are free to move as soon as they feel a force, and they're going to rearrange themselves to make sure that the electric field is very close to zero, or the potential energy of the whole cloud of electrons is minimized. It turns out that when you talk about one electron accelerating and look at one electron in this cloud, it doesn't just zip through this material. It actually goes along, and because the material has atoms, and the atoms are essentially vibrating back and forth because of the thermal energy of the material, that we know that that's what heat is. It's simply the vibration of a crystal lattice, that this vibrating crystal lattice is going to knock the electron askew. And I know it looks like, the way I drew this, the electron actually hits an atom core and bounces off, but that's not what happens. It generally hits a vibration inside the crystal lattice, and that vibration makes it go kind of like a pachinko ball or a pinball machine and follow this very zigzaggedy path. Well, every time it hits one of these vibrations, it goes in a different direction. The way we think about this is that this electron gets reset. It loses all its velocity, and it has to start all over again and get accelerated. In this case, what you find is going to happen by going through some basic physics is you know that the force on the electron is just the charge E, 1.6 times 10 to the minus 19 coulombs, times the applied electric field. That's equal to mass times acceleration, and we know that acceleration is just the change in velocity over the change in time, and just by doing a little bit of rearrangement you can calculate the velocity, or the average velocity, of an electron. So I'm going to put those little brackets around, which is the sign for average, but you think of that as the average velocity of an electron simply being the charge times the electric field it's in. These terms together are the force, multiplied by how long between collisions. The velocity is higher if tau is big and there's a long time between the collisions, divided by the mass of the electron. And remembering that our current density, J, or current per unit area, J, is simply the charge on the electron times the density of the electrons, the number per unit volume times the velocity, we can rewrite the current density J into this form right here in this yellow box. And this is actually an important equation because we lump all of these terms together to be a property of the material, because it turns out that different conductors have different densities of electrons. The mass is different in different conductors, and the time between collisions is different in different conductors. So this is a materially dependent property, and we say that J is equal to the conductivity sigma, which is this material dependent property, times the electric field. So there's a relationship between the current density and the electric field in a conductor that depends on the properties of the material, and these properties are all aggregated into something we call sigma, or the conductivity, which is given by this expression right here. Now, I've explained all of this to explain why the conductivity is finite and why electrons don't keep accelerating. And it turns out that while this is useful, we generally just look up sigma, and we don't need to know the taus and the mass of the electrons or the density of the electrons or anything like that. But the conductivity arises, and there are actually some important things about this whole equation we'll talk about in a bit. So how do we use all of this? Let's show how all of this relationship between a current density and the electric field can fairly simply lead to Ohm's law. So I'm going to basically pick a cylindrical resistor, and I'm picking this cylindrical shape because it's very uniform in geometry. And again, I'm going to basically have a positive voltage here, put 0 voltage there. By tying this to ground, we know this end is then at V, that end of our resistor is at 0 volts. Again, I'm just putting a resistor across a power supply here. We're going to make the assumption that the field is very uniform inside here, that the geometry of this is such that we have a very uniform electric field. There's no sort of spatial variation of the electric field through this structure, in which case I don't have to do any kind of integral, or I just basically can say that the magnitude of the electric field times the distance gives me my voltage difference across the resistor, which I know to be V. we also are going to assume that there's no variation of sigma, that it's pretty constant inside the material. And we know that the current, I, is just the current density times the area. If I plug sigma E in for J, just replace J with sigma E, I come up with this expression for I. And now what I'm going to do is I'm basically going to take my current I and multiply it by D, which is the length of the resistor. That's just a math trick. I can then go ahead and write D times the current this way, and notice that once I have D times E right here, I can just replace this term with the voltage, and so I come up with D times I is equal to the conductivity times the voltage times the area, and essentially what you're going to come out with is that sigma times the area, or the conductivity times the area of the cylinder, multiplied by the length of this cylinder times the voltage, will give you the overall current, or flow in coulombs per second. A little bit of simple geometric arrangement gives you this. The voltage is equal to the current times D over sigma A. This, of course, we recognize as Ohm's law, so for a cylindrical conducting material of conductivity sigma, D over sigma A is equal to the resistance of the material. Again, the resistance is equal to the length divided by the conductivity divided by the area. Does this make sense? Absolutely. It makes sense that if I double the length of my imperfect conductor, that the resistance is going to increase. It also makes sense that if I increase the area, there is going to be more area for electrons to flow through, and the resistance is going to go down. This is where we get the analogy of electricity flow like a flowing tube of water. If you make the size of the pipe bigger, more water can flow for a larger pressure, although that analogy has a lot of fallacies in it. We also know that as the conductivity gets higher, as sigma increases, it becomes a better and better conductor, that the resistance should drop, and that's actually what happens. So this equation makes a lot of sense. So essentially what we've done is we've just gone from J equals sigma E, which is one of our basic expressions of electrostatics, and let's erase that E and make it look a little bit better, and make sure we put our vector signs on top of it, that the current density is equal to sigma times the electric field, is essentially the way we express Ohm's law. And of course we have to remember that we do have an expression for the conductivity, which is proportional to the density of the electrons, the charge on the electron, as well as the time between collisions divided by the mass of the electron. And this turns out to be important because since the resistance is equal or proportional to 1 over the conductivity, and the conductivity is proportional to the time between collisions, the resistance is inversely proportional to the time between collisions. And why is this important? Why does it make a difference? Because remember that time between collisions is determined by the vibrating atoms, not hitting the atom cores. The faster those atoms vibrate, the more chance there is for collision. So if the atoms were to vibrate faster, tau would get smaller. If tau gets smaller, the resistance goes up. Well, the atoms vibrate faster as the material gets hotter. So essentially what's going to happen is you essentially put a flow of electricity through this, and some of those electrons hit the atoms, lose energy to heat. The whole material is going to heat up, and it's going to get hotter, and the resistance is going to get higher and higher. And that's why, in a nutshell, resistance is proportional to the temperature in many materials. It's also why we need to be very careful to control the temperature of electronic devices. What happens in a more general case? Well, that's pretty straightforward. Let's say we don't have a nice cylinder. Let's say we have some area A here. Well, then we go back to our expressions. We know the resistance is simply the voltage divided by the current. We know the current is given by essentially the current density J integrated over the area, so I'd calculate J for each little square and do the integral over the surface, which is shown right here. We also know the voltage is the line integral of the electric field, so a very general expression for the resistance is given by the line integral of the electric field divided by the surface integral of J. Again, we're just summing up the voltage and the current density, and just like the capacitance was determined by an equation similar to this, we see that resistance is something that's an aggregate property of the material. We can calculate the resistance essentially if we know the electric field and we know the conductivity by doing these integrals, even for structures that have very weird geometries. And remember, it's very easy to calculate the electric field if we know the voltage distribution, which we can determine numerically using Laplace's equation if there's no enclosed charge or very little enclosed charge. So again, very briefly, what we've got is that we're able to determine the resistance generally for complicated structures using this integral form of Ohm's law. This type of general formulation for the resistance for sort of arbitrary structures or non-simple geometric structures can also be used to calculate the power. And we're making some pretty big approximations here, but we can say, remember that the power is equal to the voltage times the current. We know the current is essentially just the area integral of the current density J, which in turn is the conductivity sigma times the electric field. We know the voltage is equal to the negative line integral of the electric field times the little path we're walking along. So if we go P is equal to IV and we plug in our integrals for I and our integrals for V, we can essentially write that as the first integral times the second integral, or the electric field dot product with the current density over some volume, delta V. And this is really useful if we want to find the total power dissipated inside some complex structure. It's not so easy to say, you know, if you essentially want to know the power from some weird shaped resistor, to determine that by P equals IV, you can do it, but it doesn't tell you sort of where the power is as a function of where you are in the resistor. This is sort of thinking about the power at every point, every small volume inside here, and then summing up all these volumes to find the overall power distribution. Where does it make a difference? Let's say you had something like a fuse, which is a strip of conductor with a narrow point, and you want to know essentially what the power dissipated at this point is, because where that power dissipation occurs, it's going to turn into heat. This lets you, for example, calculate a hot spot of a fuse, or the place a fuse will blow, a place in some conducting trace you might have a hot spot, because you can calculate the power at any point in space simply by multiplying this and the overall power by doing the integral. So to wrap up, let's take a look at some numbers. We've talked a lot about conductivity sigma, which is inverse ohms per meter. And there's a huge range of conductivities we find in common materials we use in electrical engineering. You know, good conductors, which are metals like aluminum and copper, have something on the order of tens of millions of inverse ohms per meter of conductivity. You can see about 3.5 times 10 to the 7th, 5.8 times 10 to the 7th for those two conductors which are commonly used in electrical engineering. Semiconductors are materials that sort of fall between the really large conductivities of metals and the very low conductivities of insulators. Silicon is a common semiconductor. You know, water you can think of as something that can have a range of conductivities. For good insulators like glass and quartz, you notice you get conductivities that are very, very low, on the order of 10 to the minus 17 inverse ohms per meter for quartz. So between quartz and a metal, there's 24 orders of magnitude difference in conductivity. This huge range of conductivity makes us do approximations to metals, and we say the conductivity is so high we call it a quote-unquote perfect conductor. And I use quotes because there really are no perfect conductors. But we make the approximation, an incorrect one, but nevertheless good in most metals, that the conductivity is infinite because it's so big, and thus metals have no electric field inside them. We also talk about perfect insulators, which is a better approximation for things like glass and quartz. And in a perfect insulator, the conductivity is zero, and no current ever flows in a perfect insulator. Good. Again, approximations, but nevertheless very good approximations in electrical engineering in most cases.